Ever wondered why DC systems are crucial in power stations? Today we're exploring the world of direct current, or DC systems in power stations, an aspect often overlooked yet integral to smooth operation. DC systems offer specific applications and advantages in power generation and control, ensuring that our power stations function at their peak. From control systems to generator excitation and even emergency backup power, DC systems are the unsung heroes of power stations. So let's dive in and find out more about the role of DC systems in power stations. DC systems are often employed in control and instrumentation systems within power stations. Imagine a symphony orchestra. Each instrument plays a crucial role, and the conductor controls them all. In power stations, DC systems are the conductors, orchestrating various components like a maestro. They send out stable and reliable control signals to different parts like valves, relays, and electronic devices. What makes DC systems the conductor's baton of choice? Simplicity and ease of manipulation. In the world of electricity, DC is the straightforward, dependable guy. It's easier to work with, predictable, and doesn't throw any curveballs like alternating current can. This makes DC a preferred choice for control circuits. Just like a maestro ensures a smooth symphony performance, DC systems ensure the smooth operation of control systems within power stations. They keep the power flowing, the lights on, and everything running as it should. In essence, DC systems ensure smooth operation of control systems within power stations. Generators in power stations require an initial source of electrical power to create a magnetic field in the rotor. That's where DC systems come into play, particularly in the excitation process of generators. But what does this mean? Well, excitation is the process of supplying an electric current to the field winding of a generator to produce the magnetic field necessary for power generation. DC systems are commonly used for this purpose because they provide a stable and continuous source of power, allowing for a consistent magnetic field. This stability is key to the efficient operation of the generator. Moreover, DC excitation systems are quite adaptable. They can respond to changes in the generator's output requirements by adjusting the supplied current, thus controlling the strength of the magnetic field. In essence, these DC systems breathe life into the generator, sparking the initial power generation process. So, DC systems are fundamental to initiate the generation of electricity in power stations. DC systems are commonly used for emergency backup power, typically in the form of batteries. Consider, if you will, a power outage. The lights go out, computers shut down, production halts. It's a scenario that can lead to significant losses, especially in industrial settings. Now imagine if there was a system in place that could instantly kick in when the main power supply fails. That's where DC systems come in. These systems, usually set up with an array of batteries, provide a reliable source of power for essential equipment during such outages or disturbances in the AC supply. They power control systems, communication systems, and safety systems, ensuring that critical operations continue seamlessly. These battery backup systems are designed for immediate response, minimizing downtime and maximizing productivity. So, whether it's a brief power flicker or a full-blown outage, DC battery backup systems are the unsung heroes, stepping in to keep the lights on and the machines humming. Clearly, DC systems are vital for maintaining power supply during emergencies. DC systems also play a key role in long-distance power transmission and in powering telecommunication equipment. Let's delve into why that is. When it comes to long-distance power transmission, high-voltage direct current, or HVDC, transmission comes into the picture. What makes HVDC systems stand out is their efficiency over tremendous distances. As power travels across large expanses, alternating current, or AC, transmission lines may experience significant losses. HVDC systems, however, are designed to minimize these losses, making them the go-to for transmitting power over vast stretches. Another advantage of HVDC systems is their ability to transmit power between asynchronous AC grids. This asynchronous transmission is instrumental in connecting separate power grids that may not operate in synchrony, facilitating a more integrated and flexible power network. Now let's switch gears and talk about telecommunication systems. Power stations often rely on DC systems to power telecommunication equipment, monitoring devices, and control systems. DC power is the preferred choice for these applications, and the reasons are twofold. First, DC power offers stability. In the world of telecommunications, stability is paramount. Any fluctuation in power could disrupt communication, leading to potential data loss or communication breakdown. DC power's constant voltage ensures a stable power supply, mitigating the risk of such disruptions. Second, DC power is well suited for electronic devices. Electronic devices often require a steady and continuous flow of power, which is precisely what DC power provides. By offering a consistent flow of electricity, DC systems ensure that electronic devices function optimally, maintaining their performance and longevity. In a nutshell, whether it's for efficient long-distance transmission or powering telecommunication systems, DC systems prove to be indispensable. Their unique characteristics, such as efficiency over long distances and stability, make them ideal for these specific applications. Thus, DC systems are integral to efficient power transmission and reliable communication in power stations. DC systems can serve further purposes in power stations, such as providing electrical isolation, and in processes requiring DC power, like electrolysis and electroplating. For starters, let's talk about electrical isolation. This is where DC systems come into play, acting as a barrier between different parts of the power station. By doing so, they help prevent ground loops and minimize interference between different systems. It's like having a bouncer at a club, ensuring that the music from one room doesn't clash with the other. Now, on to more specific applications. Some power stations may have processes that need DC power. Electrolysis, for instance, used in the production of hydrogen, relies on DC. Similarly, electroplating, a method for surface finishing, also requires DC. In these cases, DC systems step up to the plate, providing the necessary power to get the job done. So from acting as a bouncer to powering specific processes, DC systems show us they're not just about control and backup. Whether it's for isolation or specific processes, DC systems prove to be indispensable in power stations. In summary, while AC systems are dominant in power transmission and distribution, DC systems have their unique advantages. They're crucial in control systems, excitation of generators, and battery backups, providing reliable and stable power. DC systems also shine in long-distance HVDC transmission, telecommunication systems, and for specific processes like electrolysis and electroplating. They even provide electrical isolation in power stations. So next time you think of power stations, remember the crucial role played by DC systems. Thanks for watching.